Assalamualaikum warahmatullahi wabarakatuh. So today in this video we're going to talk about our final project for control system class. Um, we chose the topic altitude control of a quadcopter using linear quadratic regulator or Arqia. So we have 4 people working on this project. There's Gavin, Arqi, Naufal, and myself, Muhammad Raihan. So next, the background and motivation of the study. So quadcopter needs to stay at the right height to fly properly. But things like wind or sudden movement can make it hard to control. The altitude part of the system can be made simple using a basic model like AlkiR. AlkiR is basically a control method that helps keep the drone's height and steady and uses less power. This project shows how AlkiR can be used to control drones' altitude in real life. The system overview. So, the first one we're going to talk about the system description, which is this is a quadcopter with 4 rudders with symmetric configuration. And altitude is mainly controlled by total thrust from all rotors. And sensors like barometer, accelerometer, IMU provide feedback. The second part is the control objective. The control objective is to maintain desired altitude against disturbance like wind and to achieve smooth altitude changes with minimal energy or minimal cost. The next part, number 3, is challenges. The challenges are external disturbance and nonlinear aerodynamics, sensor noise and time delay, and balancing performance versus energy usage or cost.
Okay, so now we're going to delve into mathematical modeling and control of a quick quadcopter, specifically focusing on its vertical motion or altitude. We're simplifying things a bit by only considering the z-axis dynamics, which means we're not modeling yaw, pitch, roll, or any lateral movement. We're just focusing on its ability to move straight up and down. As you can see on the left, our foundation is Newton's second law. The equation m double dot z equals t minus mg describes the force acting on our quadcopter. And here, z is our vertical position, t is the total thrust from the rotors, our control input, and m is the mass of the quadcopter, and g is the gravitational acceleration. When the quadcopter is hovering, the thrust perfectly balances the gravitational force, so T equals mg. To make this suitable for control design, we define a new control input, U, which represents the thrust deviation. This allows us to simplify the equation to m double dot z equals U. Essentially, we're looking at two main forces in the vertical direction, the upward thrust T from the rotors, which is controllable, and the downward force of the quadcopter weight mg, which is constant. Now to the next slide. To design a controller effectively, we need to express our system in a state-space form. This is a powerful way to represent dynamic systems, especially for control applications. We define our state, z sub 1 as our position or altitude, and z sub 2 as our velocity, which is the derivative of z sub 1. From our previous slide, we had m double dot z equals u. If we substitute double dot z with dot z sub 2 and z with z sub 1, we can derive our state space equations. As you can see in matrix form, we have that bold x equals a bold x plus bu. Here, bold x is our state factor and containing z and dot z. U is our input, which is the change in thrust. The A matrix represents the system dynamics, showing how the states evolve over time without any control input, and the B matrix shows how our control input U affect the system. Finally, we have our output equation y equals c bold x. In this case, our output Y is simply Z, our altitude, meaning we are measuring our position. The C matrix defines which states are measurable, and here we are measuring the altitude. With our system in state-space form, we can now discuss the control strategy. We'll be using the linear quadratic regulator or LQR. It is an optimal state-feedback um, control method designed for linear system. Its primary goal is to minimize a cost function which balances two crucial aspects: system performance, and in our case, keeping the altitude stable, and control effort, meaning how much thrust change we need to apply. LQR is well suited for our model because our system is linear and time-invariant. It is effectively captures the core behavior of our vertical motion. A key assumption for LQR is that we have full dash state feedback, meaning we assume both altitude and velocity can be measured or accurately estimated. Let's look at the LQR overview. So, as you can see, LQR minimizes the integral from 0 to infinity of a cost function g. This cost function has two main terms: x transpose qx and u transpose ru. Q is a weight matrix on the state error. It penalizes deviation from our desired altitude and velocity. A larger Q means we care more about minimizing state errors. R is a weight on the control effort or in our case, the thrust change. A larger means we want to minimize the control in input, making it less aggressive. The design process involves three main steps. The first one is choose matrix Q and R. This is a crucial step and often involves tuning to achieve desired performance. For example, we've chosen a Q matrix that heavily weights altitude error and a small r value, indicating we're willing to exert some control effort. Solve the Riccati equation to find k. So the second process is a complex algebraic equation, and its solution P is used to calculate the optimal gain matrix k. The third one is implement the closed dash loop control law. Once we have k, our control input u is simply minus kx. The feedback law then drives our system, resulting in the closed dash loop dynamics of dot q equals parenthesis a minus bk parenthesis x.
Okay, so for the hardware implementation, there are three main electronics unit in the quadcopter systems. The microcontroller unit or MCU for the implementation of the controller, the electronic speed controller or ESC for the speed control of the brushless DC motors, and finally the inertial measurement unit or IMU for providing the orientation data for state estimation. Okay, so in here, in the image, also we can see how the hardware devices work with each other.
Hello, my name is Gavin. Now I will be explaining the code. This Python code simulates and compares the altitude and pitch control of a simplified quadcopter model using a linear quadratic regulator or LQR. The system is modeled with four states: altitude as c, vertical velocity as dc, pitch angle as theta, and angular velocity as d theta. It defines the linear state space system and computes the optimal feedback gain matrix K using the continuous time algebraic Riccati equation. The simulation includes two scenarios: an open loop system without control, where the quadcopter receives no input and remains in its initial state, and a closed loop system using LQR feedback to drive the state toward a reference target, which is hovering at 1 meter altitude and 0 rate pitch. The LQR controller calculates the control input based on the state error and stabilizes the computer. The resulting altitude and pitch angle trajectories over time are then plotted to show that the LQR system successfully reaches and maintains the target state, while the open loop system remains passive and unresponsive. Here you can see the simulation results. The plot illustrates the effectiveness of LQR control in stabilizing a quadcopter's altitude and pitch. In the open loop case, the blue lines, the quadcopter remains motionless. Its altitude stays at 0 and the pitch angle remains tilted as no corrective inputs are applied. In contrast, the LQR control systems, which are the orange lines, responds actively to initial errors. It quickly rises to the desired altitude of 1 meter and corrects its pitch angle to level, which is 0 rad. The altitude shows a slight overshoot before settling, and the pitch stabilizes almost immediately. This demonstrates that LQR effectively drives the system towards the reference state while ensuring fast and stable convergence, making it suitable for precise and responsive quadcopter altitude control.
So for the challenge and improvements, first with the challenges, first is nonlinear aerodynamics, as the actual behavior of quadcopter is nonlinear, but LQR assumes a linear model. Second is external disturbances, as wind gusts and rapid movement can disrupt altitude control. For the improvements, first, Kalman filters can be used to reduce sensor noise and improve feedback accuracy, effectively enhancing state estimation. Next, gain schedule LQR, adaptive control, and non-linear controllers like backstepping or sliding mode to better handle non-linearities.